All right, in this video, we're going to introduce solving logarithmic equations, and we're going to break this up into a couple videos for time purposes. So a logarithmic equation is one that involves logarithmic functions. So keeping with the theme of the type of equation we're solving is usually based on the main function that we're dealing with. So for instance, we have a logarithmic equation here. Log base 2 of x is 3. So notice our unknown that we're trying to solve for is contained within a logarithmic function, hence why they're called logarithmic equations. Now, in general, we want to try to isolate the logarithmic function. So in our example here, we already have log base 2 of x all by itself. There's nothing that we're adding, subtracting, multiplying, or dividing outside of this function. So that's always good when that happens. So if convenient, try to express both sides as logs with the same bases, and then equate the arguments using the equality property for logarithm. This is the logarithmic version of doing the same thing with exponential equations, trying to write the left and right sides as the same base, but maybe raised to different powers, where you can then equate the powers and solve. So same thing with logarithms. If you could write them the left and right sides as logarithms with the same bases, we can set what we're taking the logarithms of to be equal using the equality property for logarithms. Otherwise, write the log equation as an exponential equation. So go from logarithmic to exponential form. So for instance, we have log base 2 of x equals 3, and we can just as easily write this in exponential form where we take the base of 2 and raise it to the third power, and that's going to equal what we're taking the logarithm of. So 2 to the third power equals x, and 2 to the third power is 8, so x equals 8. However, please keep in mind that because logarithmic functions have domain restrictions where we can only take the logarithm of a positive number, we're going to have to check our answers that we get, because when we put them back into the original problem, we can only take logarithms of results that are positive. So please keep that in mind. And it's what we get when we evaluate what's inside the logarithm. So we might get a value, depending on what we're taking the logarithm of, we might get a value of x that could be 0 or negative, but when we plug it into the function, the result is that we're taking the log of a positive number. So always be sure to check your answers for logarithmic equations. So example 1, we're going to solve each, round our answers to 4 decimal places. We have log base 117 of 1 minus 3x equals log base 117 of x squared minus 3. And it's nice that we have two equal logarithms with the same bases, so we can use our equality property and set 1 minus 3x equal to x cubed minus 3. So we have a quadratic equation that we need to get equal to 0. So bringing over the 3x by adding it, subtracting 1 from both sides, we'll get x squared plus 3x, and then negative 3 minus 1 is negative 4. So we have x squared plus 3x minus 4 equals 0. When we solve this, we get x equals negative 4 and x equals 1. Now, looking at our values here for checking x is negative 4, if we plug a negative 4 into the left-hand side, we get 1 minus 3 times negative 4, which actually comes out to be 13. And then negative 4 squared is 16 minus 3 is 13. So negative 4 is actually okay. So even though x came out to equal a negative 4, when we plug it back in, we get the log base 117 of 13. So 1 minus 3 times negative 4 is 13, which is okay. And likewise over here, negative 4 squared is 16. 16 minus 3 is 13. We get log base 117 of 13, which is okay. So we get log base 117 of 13 equals log base 117 of 13 when we plug in x is negative 4. However, checking x equals 1 is no good, because if we look at what happens when we evaluate this at 1, 1 minus 3 times 1 is negative 2, and log base 117 of negative 2 is not a real number, it's an imaginary number. So even though the 1 came out to be a positive, when we check it, it does not hold for domains of logarithms, so our only answer is x equals negative 4. And as always, we can make sure that's correct because if we graph the left-hand side and graph the right-hand side, the only intersection point is going to have an x value of -4. They will not intersect when x equals 1. All right, example B, we have 2 minus the natural log of x minus 3 equals 1. So let's start by getting this natural log by itself. We got a 2 out in front that we need to get rid of, so we'll subtract 2 from both sides. We get negative natural log of x minus 3 equals -1. Natural logs being multiplied by -1, so if we divide both sides by -1, we get the natural log of x minus 3 equals 1. And we can rewrite this in exponential form. Remember, the base of natural logarithm is e, so we have e to the first power equals x minus 3. And adding 3 to both sides, we get x equals e plus 3. So approximately 5.7183. Now, if we check x equals e plus 3, that actually does work out because e plus 3 minus 3 is e, and then 2 minus the natural log of e does come out to equal 1. So again, also if we graph the left-hand side, we'll see that the graph of the left-hand side intersects the line y equals 1 when x is about 5.7183. So as an exact value for x is e plus 3, an approximation for it is about 5.7183. All right, so that about does for this video. Thanks for watching, and I'll see you next time.